Okay, so today what we're going to be doing is we're going to be looking at chemical reactions and chemical equations. Okay. This is the subject of section 10.1, and I'm going to go ahead and go over a few things here. First off, chemical reactions. What are they? A chemical reaction is something that occurs when two or more substances combine to form new substances. So we're starting off with some substances we already have. We combine them and they form new substances. How does that happen? Well, their atoms are rearranged and they form new substances. Actually, the atoms are arranged so that atoms of one element that were over here, now are put with another element and they combine together. So here's some examples. Hydrogen gas combines with oxygen gas and forms water. So you get the element hydrogen combining with the element oxygen to form water, which you guys know is H2O because it's made up of hydrogen and oxygen. Or here, acetic acid reacts with sodium bicarbonate. So you got acetic acid, you got sodium bicarbonate, they come together and they form new substances. They form water, carbon dioxide, and sodium acetate. So we get new stuff. Okay. Now, in order to describe these chemical reactions, we write out chemical equations. Okay, and chemical equations are basically shorthand of describing what happens during a chemical reaction. So get those two things correct here in your mind. Chemical reactions are things that happen. They are phenomena where we get new substances from old substances. Chemical equations are shorthand ways of describing what happened in a chemical reaction. So, as you can see from the first bullet point, it says chemical equations are a way of writing what happens during a chemical reaction. We use chemical formulas of the substances separated by an arrow. And on the left of the arrow, we call reactants. Reactants are the beginning substances. That's what you start off with. On the right of the arrow, you put the products. They are the new substances that were created by the chemical reaction. Okay. And when there's more than one reactant, we separate each one by a plus sign. Similarly, when there's more than one product, we separate that by a plus sign. Okay, so we'll see some examples right here. And this is kind of a final form. It's not completely final form, but this is kind of the general way that you write a chemical equation. You write the formula for reactant number one plus reactant number two, then an arrow to show that it turns into product one and product two. So here we have that first example that we showed, hydrogen and oxygen combining to form water. So H2 plus O2. We got two reactants here separated by the plus. So the plus basically separates out the two different reactants. There was only one product, so we don't need a plus on the right-hand side, and that was water. The second one right here is calcium chloride, and it's reacting with sodium carbonate. I can tell that there's two reactants because, first off, they're reactants because they're on the left of the arrow, and they're separated by the plus sign. All right, so these two things are the two reactants, calcium chloride and sodium carbonate, and they go to form two products, sodium chloride and calcium carbonate. Once again, I know that they are the products because they are on the right side of the arrow, and there's two of them because there's one plus sign, so it's separating out the two. And so here's a few more others. This is the acetic acid reacting with sodium bicarbonate to form sodium acetate, water, and carbon dioxide that we had before, and other chemical reactions right here. Okay. You can even, this is optional, but it's done a lot. You can even add states of matter in an equation because sometimes it makes a difference what state of matter something's in. So sodium and water are the reactants in this chemical reaction here. Here, sodium is in the solid state. Right? You have it as a solid. Water is in the liquid state, so you put a L. So these parentheses, notice it's subscripted. Sometimes they won't subscript them, just make them regular size, but usually you see them subscripted in parentheses. S stands for solid, L stands for liquid, G stands for gas, and AQ stands for aqueous. What does aqueous mean? Aqueous means it's dissolved in water. So like when you take some salt and you put it in water, it dissolves, right? You can go ahead and taste the salt. You know it's in there, but you can't see it because it's dissolved. So that would be aqueous sodium chloride, as opposed to solid sodium chloride, which is what you did before you dissolved it in water, right? So when something's dissolved in water, we put it as AQ, aqueous. Okay. All right. So let's see the next slide. Now, there are a couple of forms of the chemical equations. You can write it in a couple of forms. The main way of the main reason we put chemical equations together is so that we don't have to write out the whole description. Sometimes the description of a chemical reaction can take 2-3 lines, right? So we already learned before that we can, instead of writing out the whole name of a compound, we can go ahead and just write out its chemical formulas. So chemical formulas that we learned at the end of first semester are just kind of a shortcut way of writing out a compound's name. Right? Well, the chemical equation is using those chemical formulas to kind of shortcut that so that we don't have to write out things. So there are a couple of levels of the equations. There's first the word equations, where you write out the chemical format that we saw, but what you're going to use is the chemical name in the chemical equation. Now, these aren't used a lot, but they sometimes serve as kind of a step to get to your final chemical equation that uses the chemical formulas of substances, right? So you use the same rules that you use for the chemical equations that we saw on the previous slide. Each reactant is separated from the other by a plus sign. And similarly, each product also separated by a plus sign. So here's some examples of uh, a couple of descriptions of a chemical reaction that can then be turned into a chemical equation and made into a word equation. Right? So what I'm going to do is I'm going to go ahead and do this. I'm going to do a sample right here. Okay, I have written out here. I'm not going to use those other samples. I'll give you the answers to that one later on, or maybe we can do those next. But let's turn this into a word equation. Right? So this is a sentence that describes a chemical reaction. Potassium chlorate decomposes to form potassium chloride and oxygen gas. We actually saw this in one of those demos where they were sacrificing the gummy bears. Before they did that, they had to create oxygen gas by taking potassium chlorate and heating it up and having it break up into potassium chloride and oxygen. So the way we can write this is the following. Go ahead and get my pen here. Good. Okay, so let's do this problem right here. This problem right here says potassium chlorate decomposes to form potassium chloride and oxygen gas. We're going to do two things. Number one, we're going to turn this sentence here, or this description, into a word equation. And then from the word equation, we're going to come up with what we call a skeleton equation. It's a skeleton equation because it's not completely finished. But the skeleton equation is going to have the chemical formulas in there. Okay, so let's start off by trying to figure out what is the reactants and products in this form. Okay, so we have potassium chlorate decomposes. Decomposes means breaks down to form potassium chloride and oxygen gas. So clearly what we have here is this thing right here breaking down and forming this and this right here. So this is our before. We have potassium chlorate and our after. So the way I would write this is potassium chlorate. Write it up here. Excuse my writing. It's not easy to write on this little thing. 2 years and it's improved to here. So here's potassium chlorate. Right? And then I'm going to put, since it's the only reactant, I'm going to go ahead and put an arrow. And then after the arrow, I'm going to put the products. And there I have two products. I have potassium chloride. And you'll recall that chloride is and goodness. Let me go ahead and do that here real quick. Chloride is an monatomic anion, and chlorate is a polyatomic ion. Potassium chloride plus oxygen gas. I don't know if you remember, but we talked about that there are 7 elements that when they are elements by themselves, they live in pairs. So oxygen is one of them, right? They're the 7 diatomic elements, the Brinkelhoff elements, if you recall. Oxygen is one of them. So I'm going to write, oops, this is oxygen. And that's going to come into play when we turn this into a skeleton equation. So this is a word equation. And we call it a word equation because we're using words to describe the substances. Okay. So potassium chlorate is your reactant. Potassium chloride and oxygen are your products. Sorry for the sloppiness. There's your word equation. That's step 1. Step 2, turn this word equation into what we call a skeleton equation. And the skeleton equation is skeleton because it hasn't been balanced yet. And we're going to go into balancing in the subsequent equation. Subsequent lesson. But what we're going to do here is we're just going to turn potassium chlorate into its chemical symbol. And I don't know if you remember, but chlorate is a polyatomic ion. Chlorate is ClO3 with a negative charge. Potassium, when it becomes an ion, is in column 1, so it's a +1 charge. So potassium chloride is just KClO3. Okay. So instead of having to write potassium chloride, we just write KClO3. And it's going to break down to form potassium chloride. And once again, as I was mentioning, chloride is when it ends in IDE, it's usually a monatomic anion made up of 1 atom. And potassium, we saw earlier, is just a +1. This is when this is column 1. This is column 17 of the periodic table. So that's why they get a +1 and a -1 charge. So potassium chloride is just 1 potassium, 1 chloride. They balance each other out, cancel each other out. Plus oxygen. Oxygen is, once again, the diatomic element. So we don't just put it as O. Okay. Most elements you would just put their symbol. But since oxygen is one of those 7 Brinkelhoff elements, the diatomics, then we would put it down as O2. Right? Notice that here, sorry, that gets out of control sometimes. There we go. Sometimes I click on something and it gets in the way. Here, let me get rid of that. Okay. So there are, there are 7. What do I say? They were Brinkelhoff. Okay. And that is bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. They form a 7 on the right side periodic table, starting with number 7, which is nitrogen, and go to the right, then down the column with the halogens, which is fluorine, chlorine, bromine, iodine. And then you add hydrogen. So that's only 6 of them. Okay. Or you can think of them as Brinkelhoff. Okay. Whenever you see those as an element by itself. So here, oxygen is part of a compound. You just put the right number of oxygens that follow the rules for the compounds. But when it's an element by itself, you never leave it as just as it's O2. Same thing with hydrogen. If it's by itself, it's hydrogen gas. You put it as H2. Br2, I2, N2, Cl2, H2, O2, and F2. Okay. By the way, this is called the skeleton equation. On your worksheet, you are going to be asked the first few problems to turn the narrative here, or the description of a chemical reaction, turn it into a word equation. And then you take the word equation and you substitute the chemical formulas for the names, and you turn it into a skeleton equation. Okay, and that's what your assignment's going to be.